So today I would like to share with you some of my recent progress on a numerical approach to do multi-loop calculations for generic condensed matter field theory. So I would like to borrow some ideas, the perturbative renormalization technique from high energy, and apply them to solve condensed matter problems. And what makes it non-trivial is that condensed matter field theory, like Fermi liquid, usually comes with complicated interactions. And then basically we have to rely on certain kind of numerical solution. And the second is we need efficient renormalization scheme. So first I would like to thank my collaborator, Christian and Gabi, for strong support in this project. So the modern view to quantum field theory is almost all of them are like kind of effective theory defined on a certain energy scale, which we call the UV scale. And so if you do perturbative treatment based on the field theory, near this scale you will get a reasonable answer. But if you push the experimental scale like lower, sometimes your diagrams generate large parameters. For example, for 5-4 model at fourth dimension, this one loop diagram for the four-point vertex function will be logarithmically divergent. And we know how to resum those large parameters. So for example, like in Diagrammatic Monte Carlo, a common basic convention technique is to use certain skeleton diagrammatic technique, for example, Parquet equations. However, in this approach, we have to handle the fully just four-point vortex, which has 3 independent momentum and 3 independent frequency, which is too expensive to do in practice. So far, there are no Diagrammatic Monte Carlo calculation where the four-point vortex are fully just. So, but actually, the divergent piece only develops for the constant piece of this four-point vortex. So in principle, we can just resum this constant piece, and then your perturbation will be useful again. And the technique to resum part of this vortex function is basically perturbative renormalization. Okay, so to get a more systematic understanding of the large parameter in diagrams, we can use scaling analysis. So basically, if a problem has a well-separated UV scale and an IR scale, where new physics develops below this scale, then for this entire intermediate region, the system has a kind of a scale invariance. So what it means is any dimensionless vortex function can be separated into 2 parts. One part is a scale invariant part, and another part is a scale variant corrections. So this part, this scale invariant part is universal, only depends on the fixed point actually, and usually it can be quite singular in all kinds of different ways, and it's responsible. It's usually responsible for the large parameter in diagram, and this part is usually regular, and you can treat it perturbatively. And so another nice thing is this singular part, which is responsible for the large parameter in your diagram, usually can be parameterized by only relevant couplings and marginal couplings. Okay? Then, if some problem for a given problem, you can parameterize this singular part with only a few parameters. Then we can overcome the vortex problem. Basically. Right? That's the idea. And then there are several challenges to make this scheme really useful. So first challenge is how to find these relevant and marginal couplings. Then once this is solved, you know what are the relevant and marginal couplings. You know what channel, what kind of vortex function you have to adjust in to make the perturbation useful. Then you need to know how to perturbatively calculate all physical observables, and without any, you have to make it controlled. So we do not want to like throw away some correction or something. And once you know how to, once you construct a renormalized diagrammatic expansion for observables, then the next question is how to calculate this relevant and marginal couplings. So these relevant and marginal couplings are basically you have to treat them non-perturbatively. Okay, so if you treat them perturbatively, then they will become large parameters. So this talk will be organized basically by these 3 steps. So step 1 is basically find the relevant and marginal vortex functions in different field theory. So basically this is mostly like, you can find many examples in books, so I will just go through 2 simple examples, and then I will introduce some conventions. So the first example is really just the simplest 5-4 model at d equal to 4. So if you, this is a rounding scale, if you send this lambda to 0, basically it becomes a mean field type creative theory. And then you can basically in this theory you can do you can assume this part is dominating, and then you can find the scaling dimension for phi field and determine scaling dimension for u, and you can use power counting to identify the relevant piece of relevant and marginal piece in your vortex function. It turns out it controlled by 3 parameters. One is the constant piece for the self-energy. Another is the k-square coefficient for the k-square term for the self-energy, and another is the constant piece for the 4-point vortex. Okay, so I will not go into detail for the self-energy because usually we can address it with skeleton approach in numerics, so there are no big problem with that. But I will talk about how to treat this part. So basically, what we want to do eventually is to separate this singular and the universal part, and from the regular corrections. So I will define a projection operator here. What it do is, if it applies this red box on a 4-point vortex, it sends all the external momentums to 0. So then it basically projects to the constant piece of this vortex function. And if it applies to a diagram, basically what it do is it set all the external momentums, like the q here, to 0. Right? And if you calculate this diagram, you will find it's a constant and it diverges logarithmically. So this is this box basically project out the scale invariant piece in your vortex function. And another simple example basically is a liquid theory, and this is more non-trivial than the 5-4 model. Okay? So and this is an example of very typical in condensed matter field theory, because we know the effective interaction for the Fermi liquid theory, particle Hall channel effective interaction near the Fermi surface. Okay? So basically, for example, like if you do this one loop diagram for particle Hall channel, you will find that there is a singular piece develops, which is a function of momentum transfer between 2 particles, 2 incoming particles, and the frequency transfer between 2 incoming particles. And this singular function is quite non-trivial, so it will have a different value if you take the limit differently. So basically, that means when we apply this project, after we apply this projection, what it projects out is a function, coupling function, not a coupling constant. Okay? And basically, what this projection doing is several things. One thing is it projects out the particle Hall channel. So if it applies to a particle diagram, it will send it to 0. Second, it will send all external momentums to 0, all external momentums to the Fermi surface, and all external frequencies to 0. And however, it should keep the transfer momentum and transfer frequency to be the same. This is very important. Otherwise, you will change the you are not going to capture the singular piece in your vortex function. Okay? So that's 2 examples, and there are more examples. I cannot cover all of them, but they are very interesting. Problem can also be treated in a similar way. For example, the conformal field theory, and you can find more examples in condensed matter field theory books. Okay. So now, suppose like for a given problem, we know what are the singular piece in the vortex function. How to calculate physical observables. And the answer is perturbative normalization. So let me first review how people do it conventionally. So basically the idea is quite simple. So for example, with the 5-4 theory, we want to use if we use Bayer expansion to calculate the physical 4-point vertex, it will completely fail because there are logarithmic divergence associated with these diagrams. Then suppose we resum this, and then basically we can, in principle, what we need to do is to replace this expansion with another renormalized expansion in terms of a renormalized interaction, not with the Bayer one. So the way to construct this renormalized expansion is actually quite similar to the way we construct the scalar diagrams. So for example, if we want to use just the Green function instead of Bayer Green function, what we do is we take a Bayer diagram, replace our Bayer Green function with both Green function, and because this both Green function already resums all the renormalization of self-energy, so that means for any diagram we have to remove all diagrams which contains a self-energy insertion, right? So here it's basically we are doing the same. So you first take any Bayer diagram, replace the Bayer coupling with the renormalized one, and then because this renormalized coupling already resums all the UV divergence in your diagram, so that means you have to remove the UV divergence in your diagram with a counter diagram. Okay, so this becomes counter diagram. If you sum these two diagrams together, you will find it's finite. And now I introduce another symbol, which is a dashed box. It represents the finite part after renormalization. Okay, so this insight basically leads to the BPHZ renormalization scheme. There is a very very famous formula found by Zimmerman, and it basically what it says is for arbitrary diagram, you can identify all 4-point vertex subdiagram. For example, with this diagram, 1, 2 is a subdiagram, and the 1, 2, 3 is also a subdiagram. Then just do projection, like from starting with a small one and to larger vertex function. And this P projection is just the red box. So if you expand it, you will get 4 diagrams. Okay? So if you sum all 4 diagrams together, you will find all UV divergence like magically is gone. So you can even use Monte Carlo to sample these 4 diagrams. So this will be really simplified if the field theory has a pointwise interaction. Because for pointwise interaction, this box diagram are just the numbers. So that means this diagram reduced to one loop diagram, which you have already calculated with one loop calculation. So this greatly simplifies the problem, and that's the case for QED or 5-4 theory. However, for generic condensed matter problem, like Fermi liquid, this box is still a function. So you cannot just simplify it into a constant and pull it out. Okay? So you have to calculate all diagrams as they are, and very soon it's become impractical to calculate all of them. So to beat this factorial growing number of diagrams, we have to rely on certain kind of recursive algorithm to basically do this. So basically, we need some recursive renormalization scheme to take care of these diagrams, and we have to make them also possible to implement with the Monte Carlo algorithm. So basically, what I want to explain here is you can use it's possible to construct a renormalized diagram with Dyson-Schwinger equation. So the idea, so Dyson-Schwinger equation is a set of exact equations connecting different one-particle irreducible vertex functions. So for example, this equation connect 4-point vertex with the Bayer coupling, 4-point vertex itself, and the 6-point vertex. And there will be another equation connecting 6-point vertex to 8-point vertex, and there will be another equation connecting gamma 8 with gamma 10, and on. So basically, the key idea is, so we are not going to solve this Dyson-Schwinger equation. Okay? So what we are going to use is to use this Destiny string equation as a generator of diagrams. So basically what you can do is plug this 4-point vertex on the left-hand side to the 4-point vertex on the right-hand side. And this will give you one order higher diagrams. So basically it can be a generator of Bayer diagrams. The diagram comes with Bayer interaction. Okay? So suppose we can renormalize Dyson string equations, not renormalize original diagrams. Then basically we can use the renormalized Dyson string equations as a generator for all the renormalized diagrams. Okay. So this is not obvious to do, but actually it turns out it's possible to find a renormalized Dyson string equation. So let me explain the idea. It's actually quite simple. So let's start with this equation. So we move all the loop diagrams to the left-hand side. Okay? And then what we get is a inverse Dyson string equation for the Bayer coupling. Okay? Now we apply this projection on both left-hand side and the right-hand side. And let's design the projection in a way so that if it applies to a Bayer coupling, it projects to itself. Okay? Then basically we got a second equation. It's and we can subtract equation 1 from equation 2, and then we got the third equation. So the third equation relates the physical 4-point vertex with the renormalized coupling. Okay? Now we can forget about equation 1. Now take a careful look at these two equations. We find if you find one diagram for the equation for Bayer coupling, there will be exactly the same diagram for the 4-point vertex. And of course, here the diagram always comes with a solid box, and here it comes with a dashed box with the opposite sign. Okay? So that means these two equations are dual to each other. And basically, the next step you need to do is just re-expand this Bayer coupling with the renormalized coupling. So let's say we find it, and so basically the Bayer coupling will be expanded with the renormalized coupling, and this is two second-order diagrams contain two renormalized couplings. This third-order diagram contains 3 renormalized coupling, and because these two equations are dual, so even if you expand it in diagrams, these two are still dual. That means if you find a diagram here, you will find the same diagram here with the opposite sign and the different box. Okay? So then it becomes really simple to construct all diagrams. You have this equation, and you have the renormalized expansion. So for now, you do not know what is 2 and 3, but you can plug here. You can replace the Bayer coupling with this equation, replace the gamma 4 with this equation, and you can work out all the diagrams. They are quite non-trivial. So at first glance, you do not know how do they cancel. But if you expand it, it's identical to the basically to the Zimmermann's forest formula. Okay, and basically the rule now actually so if you give me a Dyson string equation, the renormalized Dyson string equation is just to replace the Bayer coupling with a solid box, and replace the gamma 4 object with a dashed box. Okay. And you need to do this for gamma 6, gamma 8 if you want to go to high orders. But actually, if you just want fourth order calculation, that's it. So basically this will contribute any diagram orders above 2. This contribute to any diagram order above 3. This contribute diagram order above 4. Okay? And of course, you can use this recursive relation to find all renormalized diagrams. But actually, in practice, if you just want to calculate the weight of this diagram, you do not have to really generate all those diagrams. You can use this as a recursive relation to calculate the weight to sum the weight of all diagrams. Basically, you can calculate the weight for this all diagram in this box and all diagram in this box, and then combine them. So you do not need to know what are diagram generated. And so this is a recursive way to calculate a recursive algorithm to calculate these diagrams. So it's following the similar essence as Ricardo's determinant algorithm. However, the difference here is with the Ricardo algorithm, you generate overcomplete diagrams and subtract the disconnect piece. here you build the diagram from a low order to high orders. So it's a bottom-up recursive algorithm, and it will have a similar efficiency for different representation like space-time, momentum frequency, or mix. Does not matter. And now it's quite easy to separate different channels because, like in Fermi liquid, we want particle channel. In superconductivity, we want particle channel. Here, it's very easy to say them. And if necessary, gamma 6, gamma 8 can also be renormalized. Okay? So because there will be another equation for gamma 6, and you can renormalize the gamma 6, and all diagram will be fine again. Okay, so since we know how to construct and calculate the renormalized diagrams, the next step, the third step, is to calculate the marginal and the relevant parameters. Okay? And then you have several choices. You can use the renormalization group, or use scalar diagrammatic techniques, or just the Dyson shrink equation itself. So the scalar diagrammatic technique actually is just this equation, because this equation relates the Bayer coupling to the renormalized coupling. So you can just solve this set of diagrams order by order. This automatically gives you something like a Parquet equation. And I will be focused on the renormalization group technique because so far there are no attempt with the renormalization group in Diagrammatic Monte Carlo community. So I will play this idea on a simple model of two-dimensional spin liquid. So the key idea of a renormalization group approach is you do not solve the problem for all energy scales. So basically you start with effective field theory at a high energy scale, and then gradually add different fluctuations at lower energy scales back to your problem. So basically what you do is you introduce IR regulator to your propagator so that the low energy part of your propagator will be suppressed at the beginning. Okay? So basically all fluctuations between these two shells will be suppressed at the beginning. And the perturbation will always very good if this rounding coupling lambda is near the UV scale. Then when you gradually lower the energy scale, you can study how this renormalized coupling flows. And eventually, when you send this energy scale lambda to 0, you recover the physical system. Okay? So you can understand it as an annealing protocol.
So physical system is Coulomb in this case?
No, not Coulomb. It's a Yukawa interaction. So it's a short-range interaction.
But when you send lambda to 0, it's a different.
Oh, sorry. This is capital lambda.
Capital lambda. Oh, okay.
Sorry. So I always fix this to be like some number, finite number. Otherwise, then it will be a short-range interacting Fermi liquid. Right? Okay. So I think basically to my knowledge, there is no like a good RG understanding of a Coulomb gas problem. For example, if you send this lambda to 0, because there are very tricky IR divergence associated with this 4-point vortex. So it's not trivial. Okay. So they are also with and basically you can that's the idea of an RG. And in the RG approach, you are not going to directly calculate the 4-point vortex itself. You are going to calculate the flow of it. Okay. So basically that's the object. That's the object you are going to calculate. And these are the diagrams. So in the diagrams, there will be always one green function. You take a derivative with like a dg over d lambda. So this will be the functional RG formulation. And this 4-point vortex can be replaced by the normalized expansion for 4-point vortex, and this 6-point vortex can be replaced with the 6-point vortex expansion. Okay? Then you can calculate this RG equation order by order. And so basically that's what I got for two-loop RG calculation for the this spinless Fermi liquid theory. And so you can and this is the RG beta function. So this object, and you can see the RG flow. essentially there will be no RG flow for high energy part, and then if the energy scale is below the transport momentum or the temperature, then the flow begins. Okay, so basically it means the 4-point vertex will remain marginal above the IR cutoff. So this has been predicted before by Shankar and many groups before. So it's consistent with the theoretical expectation. And then basically, I can compare the Bayer coupling expansion, the convergence of Bayer coupling expansion and the renormalized expansion with RG. Okay, so sorry.
What is the distance between electron compared to lambda in this?
This lambda. So I said I take it to.
No, but what is your chemical potential? Like distance between electron compared to lambda?
Oh, so I simply assume I fix the Green's function. So basically there will be no self-energy renormalization.
No, I think what he's asking is what is the product of lambda times kf?
Yes.
Oh, okay. Actually one. Oh no, not 2EF actually. EF, right? Lambda is basically the same.
Lambda times kf.
Yes. So
well, lambda is kf squared actually because it's q squared plus lambda, but lambda kf squared.
Yes.
Lambda
So
divided by
one.
kf squared
Yes.
is
yes,
what he wants.
it will be 1. Yes.
1.
I found it's actually already like following the classical Fermi liquid theory. So in priori it's not clear. It's, so I can take lambda bigger, but it makes the interaction weaker. So not that interesting anymore. Anyway, so this is a Bayer expansion, how Bayer expansion converge. So first order, order 2, order 3, order 4, so they are oscillation and it's still not converged yet. But with renormalized expansion, you can see it converge pretty fast. Order 1, order 2, order 3, order 4, and order 5 are on top of order 4, basically. So the convergence is greatly improved. And you can see why, because if you check the diagrams, like this 2-loop chain diagram, so this is not just a double diagram in RPA, because each vertex here has a direct interaction and exchange interaction. And so it's like all kinds of diagrams, bubble, vertex corrections, like ladder type of diagrams are all included here. So this diagram, if you do Bayer calculation, it will be like this red curve. But if you combine it with the counter diagrams, there will be 5 of them, and you will find it's almost identical 0. So because this is not just a bubble diagram, so this cancellation is actually quite non-trivial. But anyways, that's the reason you get a much better convergence for the series, and also that also makes Monte Carlo much more efficient, because once you combine all these diagrams, the large parameters get cancelled, so you do not suffer from sign problem anymore. Okay, so let me summarize workflow. Basically, so for a given problem, first you need to guess the relevant and the marginal vertex functions. So if it turns out, if you are lucky, you will get a finite number of them, then basically you can construct a renormalized perturbative expansion to make useful predictions. And then you need to use RG, scalar diagram, and all kinds of different techniques to calculate the relevant piece. And then you have to check whether all vertex functions now become the order of unity. Okay? So if it is yes, then basically the problem is solved. Maybe sometimes if the vertex function is order of unity, but maybe it's 2, for example, it's still large. Then you still need to use a resummation technique, like a form of Fourier resummation here. However, the key point is because you are dealing with a universal theory. So once you invent a resummation technique for one problem, you can apply it for all problems with same fixed point. Okay? And if it is not, then that means your physical understanding of your problem is not perfect yet. You have to identify the large parameter in your vertex function and go back here. Okay? And sometimes you are not lucky, and you will find there are infinite many of relevant parameters. Okay? So this is actually very typical, like for both the Hubbard model or Fermi-Hubbard model. So as long as U is the coupling, on-site coupling is larger than the hopping, larger than the bandwidth, then basically you will find the vortex function looks like this. So this is the amplitude of vortex function. This will be the rounding scale. So you can do power counting about. So basically the t is below u. Okay, so that's the on-site coupling. And basically you can do a power counting about this u, and you will find all 4-point vortex, 6-point vortex, 8-point vortex. The constant piece are all relevant, and the first derivative of frequency are all marginal. So then basically that means indicates you cannot truncate the Dyson shrink equation. You have to keep it all vortex functions. You cannot solve this problem with truncated diagrams. But maybe like if you try to use some non-perturbate shift, like shift from DMFT solution, for example, maybe you can penetrate this barrier. But if you want to solve this problem with Dyson shrink equations, I don't think it's possible actually. So I will say this is a scale barrier. So even if the low energy physics is very simple, it's 5-4 model, for example, you cannot see it. Okay. So how to handle this problem? So basically, there are way out. Basically, what you need to do is integrate out the local degree of freedom exactly with a non-perturbative method, like impurity solver or ED. Then, based on the solution of ED or impurity solver, you construct effective field theory. So this effective field theory really address the relevant degrees of freedom in the IR limit, and then you can go to here to solve this problem. Okay. So that's the workflow. Okay, that will be my talk. Thank you.